Hi there, my name is Shivdat, and today we're going to be looking at an interesting problem in physics to compare the strength of the gravitational force to the electromagnetic force acting between a proton and an electron. The distance they are apart is not specified. We'll see why that's not important in a minute. But before we begin, let's just recap the four main fundamental forces of nature in physics. There is the gravitational force, there's the electromagnetic force. Gravity attracts bodies together, anything that has mass. The electromagnetic force can be attractive if it's between particles of opposite charge, or repulsive if it's between particles of the same charge. Charges are negative and positive. There's the weak nuclear force, and then there's the strong nuclear force. So really that's all the four fundamental forces of physics, and all interactions arise through them. Now we're going to look at a problem. Supposing a proton and an electron are distance r apart. How do you think the force of gravity, the gravitational pull between them, to the electrostatic attraction between them compares? Which is stronger, and by how much? So let's actually do the calculation to figure this out. We have, on one side, let's just label a few constants, the values of a few constants that we're going to use in our calculation. We have the gravitational constant, G, equal to 6.67 into 10 to the negative 11 Newton meter square per kg square. We have the mass of a proton is basically 1, and the mass of an electron. The mass of an electron is 9.1 into 10 to the negative 31 kgs. The mass of the proton is of the order 10 to the negative 27 kgs, and the coefficient is 1.67. This is going to be used in the calculation of the gravitational force of attraction between them. Now for the electrostatic force, we know that the constant K is 8.9 into 10 to the 9 Newton meter square per coulomb square. And then we have the charge on an electron is negative 1.6 into 10 to the minus 19 coulombs, and the charge on a proton equals positive 1.6 into 10 to the minus 19 coulombs. Now we know from Newton's law of gravity that the gravitational force between two objects is G, m1, m2 by r squared, where m1 and m2 are the masses of object 1 and 2. R is the distance between them. And similarly, give this a subscript G, it's the force of gravity. And similarly, the electrostatic force, or attraction or repulsion, is K, Q1, Q2 by r squared, where K is this constant, Coulomb's constant, Q1 and Q2 are the two charges. So let's forget the coefficients, let's just look at the powers of 10 to get an order of magnitude estimate. We have G is 10 to the negative 11 into m1 into m2, 10 to the minus 27 into 10 to the minus 31. Similarly, this is going to be 10 to the 9 into 10 to the minus 19 into 10 to the minus 19. So I'm going to erase this little diagram at the top and carry out the calculation up top. So Fg, force of gravitational acceleration, is of the order 10 to the negative 30, 40, 50, 60, 61, 62, plus 7, 69. 10 to the negative 69. Notice we've forgotten about the coefficients, we're just taking the powers of 10. Similarly, the electrostatic force of attraction is of the order 10 to the negative 38 plus 9, that's 10 to the negative 29. In other words, the electrostatic force divided by the force of gravity is 10 to the minus 29 upon 10 to the negative 69 which is equal to 10 to the 40. So in other words, the electrostatic force is 40 times, 10 to the 40 times more powerful than the gravitational force, which is a huge number, mind-boggling number. Perhaps even, that number may very well be more than the number of atoms in our universe. So what does this mean, really? Well, there are numerous ways where we see this. For example, say you were to jump off, say I was to stand on the table in front of me right here and jump off into the ground. The force of gravity of the earth is attracting me towards its center. But why don't I get pulled towards the center of the earth? Common sense tells me I'll stop, I'll hit the floor and I'll stop. But what is it that's stopping me? It really is the force of repulsion between me, my body, and the ground. The electrostatic force of repulsion, which prevents me from going down, 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 all the way to the center of the earth. So what we feel as resistance of some body is really nothing but an electrostatic force of repulsion when we're getting too close. Similarly, we can see that basically at a small scale, at a really small scale, which is the quantum world, gravity has almost no effect. In fact, in quantum mechanics, we don't even take gravity into account because gravity is so small it's negligible. While on the other hand, on a large cosmic scale, when we're dealing with planets and asteroids and objects of that scale, which are neutral, right? They have usually an equal number of electrons and protons, or perhaps a very small difference. And they have huge masses. In that case, gravity takes effect and is the more dominant force there. Even though, per kind of per particle, it would have a much smaller effect than the electrostatic force. And so, string theory, which is kind of being claimed to be a theory of everything, aims to combine these two theories. It's radically different theories: quantum mechanics, which governs the law of the small, and general relativity, which governs the laws of the heavens of the large, and basically kind of unite this gravity, incorporate gravity into quantum mechanics, which is usually ignored because it's just so small, 10 to the power 40 times smaller than magnitude. Notice the distance didn't matter because the r squared cancelled out when we divided fg by fe, and these two should have been divided by r squared, but when we take the ratio, that r squared cancels and we get 10 to the 40. I hope you enjoyed it. Thank you.